Hello, hello. Bum, bum. Na, 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 na. खाली 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 है सब. Just a second, guys. Ba-bam, ba-bam. Hello, hello. Yes. Alright, so uh, हमने कल longest substring without repeating character तक कर लिया था. Longest repeating character replacement का हमने most of the part कर लिया था. Now the only thing which was left yesterday was its edge cases. So वो हमें आज सॉल्व करने हैं. एक्चुअली सॉल्व नहीं करने हैं, हम उसका सॉल्यूशन ही देखेंगे. कल तो अपना कुछ नेटवर्क इशू आ रहा था, इस वजह से मैंने स्ट्रीम ही बंद कर दी थी फिर बाद में. सो लेट्स सी टुडे इट्स सॉल्यूशन quickly and then we will move forward. Okay, cause यार कल ऑलरेडी है ना 1 घंटा इसमें ही खराब हो गया था, इसलिए. Let's go, let's go, let's go. I'll go with the video first. No,
Hey everyone.
let's go with the solution, with the code. So in brute force he has used 2 loops. Okay, the hint big of m is the space and n in time. Which character would you replace in a string to make all its characters unique? Can you think with respect to frequency of the characters? Exactly. It's always optimal to replace characters with the most frequent character in the string. Uh, in the string, why? Because using the most frequent character minimizes the number of replacement required to make all characters in the string identical. How can you find the number of replacements now? It's always the optimal replace characters with the most frequent character in the string. Why? Because it will minimizes the number of replacements required to make all characters in the string identical. The number of replacement is equal to the difference between the length of the string and the frequency of the most frequent character in the string. A brute force solution would be consider all substrings, use a hash map for frequency counting, and return the maximum length of the substring that has at most k replacements. This would be an uh, big of n square solution. Can you think better? So he's basically recommending us to create a hash map and count for the characters which has the maximum frequency within the string, and uh, yeah, but in our solution we were not using any hash map. We were able to pass somewhere around 400 test cases, and it was half of the test cases which were there in total. So uh, if we can do that, and we're just stuck in some edge cases, so we can go for the solution which he has used. This is the brute force, this one is the sliding window and optimal sliding window. Let's see for the sliding window part. He has used hash set character. I have also used hash set at that time. If you can go back to my previous video of yesterday, so in that I have used at first the hash set only, and then I have switched it to uh, array list because I thought that I can contain frequent characters within that array list and can use that, but he has used this. Let me open Excali dropper, Excali, whatever it is called. All right. All right. So uh, let's go for the video. No, we were at this solution. Character replacement. He has used res integer has set, and then he c to char array, and he added all the unique characters to the hash set. Then he ran for loop count. He has used if the character is equal, then he was incrementing the count of the solution, while r is small, r minus plus 1 minus count is greater than k at that time. Do this. Let's go for the video itself, so we won't be.
Everyone, welcome back, and let's write some more NeetCode today. So today we're going to solve longest repeating character replacement. And so this is another problem from that blind 75 list. So we are going to be one step closer to completing the entire list. The link will be in the description to this spreadsheet if you do want to take a look. And hello to the 6 people that are currently viewing the spreadsheet right now. You're going to be in the next video. But okay, so let's get into this problem because it's another pretty fundamental problem that's really good to understand. So we're given a string s and a single integer k. And so basically they tell us that we can choose any of the characters in the string and change it to any other uppercase English character. So in this problem, every character in the input string is going to be limited to uppercase English characters, and we know that there's 26 uppercase English characters from capital A to capital Z. And so basically we can perform a replacement on any of the characters at most k times. So we're allowed to replace k different characters in the string to any other character we want. And what we want to do is return the length of the longest substring containing the exact same character we can get after performing at most k different replacements. So we just want to return that length. We don't actually have to make those replacements in the input string. So in this case, when we take a look at the input string, we have A, B, and we're allowed to replace 2 of the characters. So what's the longest substring we could get with the exact same character? Well, we could replace one of the B's. We could basically replace both of the B's with a capital A, and then we get 4 A's in a row, which would give us an output of 4. And we could technically also do the opposite. We could replace the A's with capital B's, and that would give us the exact same result, a length of 4. So I'm going to show you how you can solve this problem in big O of n time, and technically it's going to be big O of 26 multiplied by n, which we know is also reduces to big O of n, but there's actually technically an easier way to do it, or at least a more simple way to do it, which is just going to be a flat big O of n. We don't even need this 26 constant. But this way is actually pretty tricky to get to, so I'll be going over a little bit of it, but this is kind of the main way that you'd want to solve this problem. So let's say we're given an input string like this, and we're given a k value. Now the most brute force way would just be check every single substring, right? And if we were checking every single substring in the entire input array, we know there's n squared substrings, so that wouldn't be the most efficient way to do it. But even if we were doing it like that, what exactly are we looking for? If we're looking at a particular substring, how do we know if this substring is valid? Because remember, at the end of the day, we want to maximize the result, right? The result is going to be the longest substring that contains a single character, and we can make 2 replacements. So let's look at this substring alone. How do we know if it's valid? Well, which character are we going to replace? Are we going to want to replace the B's in order to make it all be to match A? Or would we want to replace the A in order to match it with the rest of the B's? Of course, we're going to replace the character that occurs less frequently, right? Because the number of replacements we have is limited, so we would want to replace the characters that are less frequent. So in other words, we want all characters in a particular window to match the most common character in that window. So what we're going to be doing is we are going to have a hash map or a array, which is going to take every single character. In this case, we only have characters A and B, and we're going to count the number of occurrences of each character. So for example, if we were looking at this substring, we see that there's 3 B's and we have a single A. So how do we know if this window is valid? What we're going to do is we're going to take the length of the window, which is going to be 4, right? We're going to take the length of the window, right, which we know in this case is 4, and we're going to take the length or the count of the most frequent character. In this case, we know that that's B, and the count of it happens to be 3, so we're going to take 4 minus 3, and from that, we're going to get a 1. Now, what does this value 1 tell us? It tells us the number of characters in our window right now that we need to replace in order to make it match the most frequent character B, right? We have a B here. We want everything to match a B. In this case, we only have an A, right? But it could be possible, like, who knows, maybe that we would have a C over here, right? Or an X over here. And it doesn't really matter what the characters are. We just know that B is the most frequent character in the window, and the other characters that are not B, A and Z, for example, are the characters we want to replace. So we can calculate the number of characters we want to replace just like this. And so we want to replace 1 character. How do we know if we have enough replacements to do 1 character? Well, of course, that's our input parameter k, right? So what we're confirming here is that this value is less than or equal to k. As long as this condition is true, that means our current window is valid. That means we have enough replacements to make those replacements in our current window. So this is the main condition that we're going to be checking. The other question is, how are we going to know which character is the most frequent? Well, the brute force way is going to be taking a look at our map of counts, and we know that the max size of this could possibly be 26 because we'd only have 26 different characters. So finding the max character is going to be big O of 26. So that's a little bit more inefficient than we would like, but it's technically still linear time. Like the overall algorithm is still going to be linear time. The last thing that we're going to have to do though is to this equation, we're going to have to add a sliding window technique. So basically what what we're going to do is we're going to take our window, start at the beginning, expand it as much as we can, as long as the condition that we mentioned is valid. If the condition is not valid, then we're going to take our left pointer and then shift it as well until the string becomes valid once again. So we're going to have a left and right pointer. So initially left is going to be at the beginning and right is also going to be at the beginning. And also the counts of A and B are initially going to be 0. Now we're going to look at the first character, right? That's where our right pointer happens to be. We're going to look at it. We're going to say, okay, we have a single A, right? We're going to take our count of A and set it to 1 now. So is this window valid? As in, can this window be the exact same character within 2 replacements? Of course it can, right? That's kind of the trivial case, but we would still calculate it. And the way we would calculate it is get the size of our window. Right now we can see the size of our window is 1, subtracted by the count of the most frequent character. In this case, we know the most frequent character is A. 1 minus 1. Is that less than or equal to K? We know K is 2, so of course, this is going to equal 0. 0 is less than or equal to 2, which is K, right? So of course this window is valid. That's kind of a trivial case. Next, we're going to shift our right pointer to the next character, right? So now we have a B, so we're going to increment the count of B in our map. So B is now going to be set to 1. In this case, the length of our window is 2. The most frequent character is either of these, right? And the count of that frequent character is going to be 1. So we're going to get 2 minus 1 equal to 1. So this is the number of replacements that we would have to do. And looking at our current window, that makes sense, right? We'd have to replace at least one of these 2 characters. So we're going to ensure that the number of replacements that we need to do is less than or equal to K, which is 2. Of course, that's true. So our window is currently valid. I guess I did forget to update our result. So since this window is valid, the length of the window is going to be set to the result, right? So right now the result is 2. 2 is the length of the longest window that we can get. So that's our result for now. So now let's continue. Next, we're going to shift our right pointer to the third character. So now we get another A. So we're going to take the count of A and increment it all the way to 2. And we're basically going to repeat our algorithm. So once again, we're going to get the length of the window 3 minus the count of the most frequent character. We see the most frequent character is A. So the count of it is 2. 3 minus 2 is 1. Is that less than or equal to 2, which is K? Yes, of course it is. So this window is also valid. We can update.
Sorry guys.
Our result now to 3. So we found another window even longer. So I'm going to take our right pointer once again and then shift it over to the B. So now we're going to be, since we reached another B, we're going to increment the count of B to 2 now. And so the length of our window now is 4, and the count of the most frequent character is either of these, and that's going to be 2. 4 minus 2 is equal to 2. Is that less than or equal to K? K is 2 in this case. So of course, once again, this condition does hold. So once again, we found a window that's longer than our result. We found a window now of length 4. And so once again, we're going to take our right pointer and shift it. So now another B, let's increment the count of B to 3. So the length of the window now is 5 minus the count of the most frequent character. That character is B. 5 minus 3 is this 2, and less than or equal to K. Of course, it's still true because when you look at our window, we have 3 B's. So that means we're going to be replacing the A's. So we're going to need to make 2 replacements, and we are allowed to make 2 replacements. Okay, so now we're finally going to get to the case that I mentioned earlier where we're going to have to take our left pointer and then slide it to the right, which is why this is a sliding window problem. So now we reached an A, so we're going to take the count of A and set it to 3. So now we have A count 3 and B count 3. So let's take the size of our window, 6, subtract from it the count of the most frequent character. It's going to be either of these, so 6 minus 3 means we need to make 3 replacements. Is that less than or equal to K? K is 2. So we exceeded K, right? We exceeded the number of replacements we're allowed to make. If we wanted this window to be valid, we have to replace 3 characters in it, but we're not allowed to do that. So what we have to do is shrink the size of our window until we are valid. So we're going to take our left pointer and shift it to the right. So now the left pointer is going to be over here. It's going to be at the B. So since we removed this A from our window, we have to decrement the count of A in our window. So I'm going to cross this 3 out, and now it's actually going to be set to 2. I kind of ran out of room, but I hope this is still readable. So now the count of A is 2. So now let's once again check, is our window valid? Well, the size of the window now is 5, and the count of the most frequent character is B, and that's going to be 3. So 5 minus 3 is going to be equal to 2. Is that less than or equal to K? Yes, we are once again valid. So this is technically a valid window, and I think I forgot to update the result earlier when we had a window of size 5. So the result right now would be size 5 because the longest window we can make is either this window or the window that we had earlier with these first 5 characters. But yeah, and so at this point, we would stop our algorithm because we did find a window of 5 that is valid, and our right pointer cannot be shifted anymore. So this is the general algorithm. So it's a fundamental sliding window problem with this particular condition being important. But there's actually one way you can do it without having to look through the entire hash map every time you want to find the most frequent character that occurs. And it's kind of tricky to arrive at this solution, but it's pretty easy to implement once you can figure it out. I'll explain the algorithm at a high level. I don't want to waste too much time on it, but basically we're going to be having another variable, and it's going to be called max frequency, basically the count of the most frequent character at any given time. So basically, for example, if we had A as a count of 3 and B as count 2, we'd say, okay, the count of the most frequent character occurs 3 times, so max F is going to be 3. And so anytime, if we got a B, let's say we incremented our B all the way up to 4, then we'd want to update our max frequency to 4, right? So we'd always want this to be the most frequent character. Now, the one problem is if we're trying to maintain the count of the most frequent character, what happens when we take our left pointer, for example, right, and then shift it, right? When we do that, we're basically removing a character, and therefore we're going to have to update our count map, right? We are going to do that. And if that does happen, right, let's say we took B and then from 4, we decremented it all the way down to 2, for example. Then we'd have to rescan this entire map and then find, okay, what's the new most frequent character, right? So we'd have to take our max frequency and from 4 downgrade it all the way to a 3, for example. So then we'd have to set it to a 3, and that would basically defeat the purpose, right? We'd still have to do that big O of 26 calculation to scan through this, but it's technically true that you don't have to decrement this max frequency. But the main idea is this. The result is only going to be maximized as we find a new max frequency, right? Because remember what we were doing. We were taking the length of the window subtracted by the max frequency, right? Whatever the most occurring character was, and we wanted to minimize this, right? So basically we want the length to be maximized because that's what our result is going to be set to. So therefore, we also want the max frequency to be maximized because we want to ensure that this is less than or equal to K, and K is going to be a constant. So for example, let's say I had a max frequency of 4, but let's say now the new max frequency got downgraded to a 3. I'm still going to leave this as a 4 because it's not going to change our result. Because for example, if I had a 6 minus 4, that was less than or equal to K, which is 2 in our example. And if I leave this as a 4, I'm basically overestimating what the max frequency is, but we know at least at one given point in time it was a 4, so therefore we were able to take the length 6 and then set it equal to our result. And now, if we're ever, so let's say our result is now 6. If we're ever going to increase the result from 6 to another number, like for example 7, we would require our max frequency to increase. If it stays the same or if it decreases, our result is never going to change, because we only change our result when we increase our max frequency, because that's the only way this condition here is going to be true. So if our max frequency is downgraded, we don't have to actually update it. We don't have to look through the entire hash map to find the new max frequency. But if we increase our max frequency, for example, if I took this A and then from 3 I set it equal to a 5, then that's something we can check in big O of one time. And then if we increase this, then we definitely do want to update our max frequency and increase it. And that's something we can do in big O of one time. So I know I probably went a little too long into this, but the main idea here I'm trying to get at is the easy way to solve this problem with a sliding window is going to be big O of 26 times n, which is technically linear, but there is a clever way to do this in big O of n time that honestly I didn't figure out on my own, and I wouldn't really expect other people to be able to figure it out on their own, like in an interview at all. But I will show this, the standard solution, and I'll also show the code for this more optimized solution. Okay, so now let's jump into the code, and the code is actually a lot easier than the visual example that I gave, a lot shorter for sure. So we're gonna have a hash map to count the occurrences of each character, and we're also gonna have a result, which is gonna tell us the longest substring that we can create with k replacements. And we're gonna have a left pointer, which is gonna be at 0, and then our right pointer is gonna go through every single position in the entire string S. So what we're going to do is for the character at position R, we're going to increment the count of it. We're going to take 1 plus whatever the count currently was, count.get this character. And if the character doesn't exist in our hash map, we're just going to return a default value of 0. That's what this function is doing. And so before, what we're going to obviously do is update our result, right? And we want to set the result equal to the max that it's ever been, and set it basically equal to the size of the window. We can get the size of the window. So we're going to take the max of result and the size of the window. The size of the window can be gotten with right minus left plus 1. But before we do this, before we update the result, we want to make sure that the current window is valid. So what I'm going to do is basically say while, and I don't think you would actually need a while here. You could just do if, but I'm just going to do while just because. So while the window is not valid, and we would know that by taking the length of the window, which we have down here, so I'm just going to copy and paste that, the length of the window, subtracted by the count of the most frequent character, which can be gotten with max of count dot values, right? We're basically going through the hash map, which could be size 26, and just getting the max value from it. So this is the number of replacements that we have to do. And if the number of replacements was greater than the number of replacements that's allowed, which is equal to k, that's when we would want to shift our left pointer. So we'd want to increment our left pointer. But before we increment the left pointer, we'd want to take the count of the character at the left position and then decrement it by 1. And that is the entire algorithm. After all of that is done, after we've gone through the entire string, then we can just simply return our result. And as you can see, this is pretty efficient. It's linear time. It's about as efficient as you would need, I think, but I'm going to make that slight optimization that I showed you. I'm going to maintain the max frequency in a single variable so that we won't have to do this operation where we're getting the max of the entire hash map. Instead, up here, before we execute that loop, I'm going to say max frequency is going to be equal to the max of what it currently is, max frequency, or it's equal to the frequency of the character that we just added a value to. Maybe that character became the most frequent character. So we would have to update our max frequency, and we can do that just like this. And this is a constant time operation. We're not scanning any list or anything. And then once we have this max frequency, we can use it in this loop execution, right? So we can replace this and just use max f for that. And the thing is, notice how even when we're shifting left, we're incrementing the left pointer, we're potentially removing characters from our window, we're still not decrementing max f because we actually don't need to. It won't end up affecting the result if we just don't decrement it. And that very slight optimization, which is really simple in terms of code, but it's kind of hard to see why we're allowed to do that. Watch how much more efficient it makes our algorithm. So as you can see, look, it definitely improved it. I think it was 50 milliseconds difference. So this is significantly faster. It's hard to see why, though. I would definitely not expect most.
Alrighty. Bro, I haven't even used that thing. I'm still failing. That's why. Yeah. So, what he does was he used a hash map. Character integer int of r is also 0. Alright, and the count or the length, let's say max length equals to 0. Then uh, the formula he said, like the formula he talked about was this one actually. So we will be incrementing the maximum length. Yeah, so maximum length will be but before than that we need to check first that if math if yeah, area, which is left minus right plus 1, the length of the window minus max of L is smaller than K. At that time we need to decrement the pointer L, right? And we also need map dot get s dot character at of L, or we can use this map dot get s dot char at L put if absent, right? Not map dot get this plus equals to, sorry, so we are decrementing its frequency, okay, but we are not decrementing uh, the max the maximum frequency of this, and we are checking the maximum frequency by math dot max of maximum frequency and the frequency of map dot get map dot get s dot char at r. Okay, before than that we are also incrementing map dot put yeah, sorry guys. Okay, so we then be also incrementing map dot put map dot get or default as character of this plus 1, right? Okay, then we will be increasing the frequency we get. Okay, if it is greater than, it will be going to get replaced. Okay, so at both of the time we will be incrementing the frequency as well. Then we will be incrementing the length as well, so it will be not maximum length, bro, it will be uh, frequency. Okay, so is greater than, while this is greater than k, at that time the L will shift and this will shift as well. Okay, so we will be having math dot max of L and R minus L plus 1 minus maximum frequency. Alright, and at that time we will be having our max length right? And then we will be incrementing our pointer. This won't be the case. The case will be r will be smaller than s dot length, and we will be also incrementing this, not to be decrementing. Let's try running this solution. What we got? Null pointer exception. Oh yeah. Oh, sorry. It needs to be R, right? Not this. So expected was 4. We got 2 only. And why was that a case? Smaller than R, while R minus L plus 1 minus this is greater than K. At that time only we will be putting that character's frequency at the minimum, and then we will be incrementing the L pointer, and here at R we will be incrementing the frequency. Here we will be getting the maximum frequency from that character. Okay, the maximum length math max. Let's see what wrong we have did. So hash map and as small than our count dot put. See, he did this part at first, okay, and then incremented. Then while this is greater than, then he had done this, and at the end he did this. But okay, so at only this time he is using this. Okay, so if I also don't use this, then it will be solved, I guess. Hmm. All right. So, but why he haven't used? Okay, cause he only wants to. Uh, this was for the maximum frequency, right? Like how many times he had to replace the characters. That was the only point he used this uh, formula. Okay, and this is only for the length. Okay, so how broader the length he got. So that's the thing here, and we have passed this test case as well. Now we are still having a pending work, which is updating the sheet we were maintaining. Let me show you DSA. Where is the DSA? Yeah. So this was the sheet. What? I I had it added all other. I don't know what happened, but so we need to. Okay, guys, I will update this sheet and I will add it in the upcoming. I will add this sheet in the description in the upcoming videos, maybe tomorrow only. So, what I'm doing in this sheet is I'm uh, adding all the questions which are there solved by me, and I'm writing down their approaches. So this will be better for you at the preparation time at the interview, before than that. So you can revise through the sheet easily. Okay, so like for the threesome, I have did this like aim for big of n square time complexity, use for loop for iterating over the array, and use two pointers ln r to find some combinations to eliminate duplicates. You can sort the array first. So this is very helpful. Okay, so I will be updating that. So we have done this question as well. Okay, longest repeating character. Keep this uh, thing in mind. Now, permutation in string. Oh my god. This question is at a level, bro. So, permutation in string. Let's read the description. Given two strings s1 and s2, return true if s2 contains a permutation of s1. If s2 contains a permutation of s1, or false otherwise. In other words, return true if one of s1's permutation is the substring of s2. uh, you guys might have got it or not, but let me tell you. So let's say we have this s1 and this string can be permuted into other string as well. Like for this we can only have a permutation of ba. So permutation is the uh, like juggling of words, I would say, characters. Uh, so like AB can be converted to BA. In that way, ABC can be converted to ACB or BAC or BCA, like that. Okay, so here AB uh, like permutation of AB should be there in the string BA, in the string of this S2. So there is a permutation which is BA. So uh, if we find it, we will return it true. Otherwise, we will return false. So here, if we if we will see that, do we have its permutation in here? Then no, we don't have. At that time, we will return false. Although we have the same characters present in this string as well, but yet it is uh, not here. I mean, this is not making a substring. All right, so let's use this part one first. All right, so we have an input S1, AB, and S2, uh, EIDBAA, DB8000. So at this time, what we will have in our mind, like the first approach we get is we will take the count of both the characters in first string. We will create a window by using left and right pointer L and R, and we will create that window till the length of the uh, S1, right? And we check that if that window contains the same number of frequency in the S2 or not. That's the most simplest approach we can have first. So let me walk you through the solution from here, and then we will code it first. So in the first iteration, like in the first iteration, let's just see, check this one. So A will be having only one character, B will be having one character. Okay, and then in the second iteration, what we will do, we will go to iterate S2. Okay, and we will be checking the like the window if that if these two elements resides in S2 or not. Okay, so let's create this. Okay, E, let me make it bigger. I hope you guys can see it. Oh, got it. Let's just do it this way. E I D B A O. All right. So we will make this one. Now what we will do, we will create a count. We will create two pointers. One is left, second one is right. Okay, and we can we will do it like this only because we will be needing to have a count of the characters which are there in the window. Okay, so right now there is no window because its length is 0 for now, or let's say 1. Okay, so we will gonna be creating the length till how much, till the size of s1 string. So at this time we will create a count of s2, let's say. Sorry for this because I don't have any trackpad, so I need to use it, draw it with the mouse only. So at this time we have e, and we have e of uh, size 1 or e of frequency 1, and we will check if this e is present in this ab or not, or if this AB is present in this window or not. First, it's not even the valid window, so we will go for making the valid window first. Valid window will be the size of this S1. So we will shift our right pointer, and we will also gonna be updating I with 1. Okay. So at this time we got the right window. We will check if these characters are present in the string as well. Then we will say no, it's not present. But here is a catch. I just got it, that while, like, after creating this window, you can't just directly check this array with the array of this. So instead of that, we will be keep shifting the left pointer as well while decrementing the leftmost character frequency. So at this time we will check. Let's go back first. Let's go back. So what will happen here? Yeah, so we are still at E. Okay, at this time what we will do, we will check if this is present in the count of, or the frequency of, or a hash map of this frequency table. Okay, at this time it is not present, so we are going to be shifting both, or let's say shifting first. Samuel, when you go, Magu, sorry bro if I can't like pronounce you right, but hi, how are you? Okay, so at this time we're gonna be incrementing our pointers because this doesn't have the right character, which should be there in our hash map. So we have shifted our pointers. At this time we have decremented it to 0, and we have put new character to 1. This time we're gonna be checking if this character is present in our hash table. So no, it's also not present in our hash table. So at that time we going to again be shifting our pointers. Okay, this is left and this is right, and we also gonna be decrementing our pointers here. And after then we will be shifting. Okay, so we have shifted the pointer already. We're gonna be adding d to the frequency of 1. Gonna be checking in the hash table if they are present in this or not. So no, d is not present. We're gonna be decrementing its frequency and come on the second part, I mean second character. At this time we got b. Okay, and now we're gonna be checking if b is present in the hash table. Then yes, it is present. Then we're gonna be shifting the right pointer only. Okay, which is a, and this is a. Yeah, so this is a. Okay, and at this time we we are also having the right uh, frequency of the characters and the right length, I mean the right size of the table, right? So at this time we're gonna be uh, we are known to this situation that these both characters are present in the hash table of S1 within the same length. Okay, so it won't be like this, like you also need to check that the frequency should be also same at this time. So let's say if I have this let's say uh, let me do this one. So if I have one more b here, okay, and sorry, we have this. Okay, yeah, So we have just shifted our B and we check that B1 this one uh, so the frequency of B is present there uh, in the S1 hash table. So at that time it's uh, like valid. Then we will shift our R again, and at this time it will increment uh, the frequency of B to 2, right? So because of that it won't be a valid character in the S1 hash table. So because of that we want to be uh, uh, using this B, and we will be shifting our left pointer, and we will shift that left pointer to the right side until and unless that counts become again 1. So for that we will come here, and at this time it's 1 at the and now then we will gonna be again shifting this to A, so we got the valid uh, at this time we got a valid solution, right? Now let's go here. If I can't make you understand in this diagram, okay, because I'm getting some like I'm not able to convey you this properly through this diagram. Let me code it for you, and at that time you will be able to get the thing what I'm trying to say to you. So we will be using hash map uh, so of same character and integer map of s1 equals to new hash map. All right, then we are also going to have a map of s2, right? So because we need to check their sizes, right? uh, okay, and now what we want we want two variables called left and int of r equals to 0, and while why always I get this problem.